Let's study the entropy of Hawking radiation. George, this is the big one. The review by Almheiri, Hartman, Maldacena, Shagulian, and Tajdini from 2020. I want to really understand it, not just nod along. And I want the mathematics, because I'm building black hole analog simulations on cold atoms and quantum hardware, and I need to know what curve I'm actually trying to reproduce.
Perfect framing, Alice, and I promise we'll do the math out loud, step by step. The whole story is about one plot, a graph of entropy versus time, and the shocking claim that gravity, computed carefully, gives you a different curve than Hawking got in the 1970s. That difference is the resolution of the information paradox. By the end, you'll know exactly why the curve turns over, and where in your cold atom setup that turnover should show up.
Let's build up to it properly. Start me at the very beginning. What does it even mean to say a black hole has a temperature and an entropy?
Right. So in the 1970s, people noticed something curious. Take a rotating black hole. If you drop a bit of mass into it, the horizon area responds. And the equation governing that response is kappa over 8 pi g Newton times the change in the area equals the change in mass minus omega times the change in angular momentum. Here, kappa is the surface gravity, omega is the rotation rate of the horizon.
And that looks suspiciously like a thermodynamic law.
Exactly like one. Compare it to the first law of thermodynamics. Temperature times change in entropy equals change in energy, minus the work term. Line them up and you're forced to guess that the temperature is proportional to kappa, the surface gravity, and the entropy S sub BH is proportional to the area of the horizon. At first, this was just a formal analogy, a rewriting of Einstein's equations in suggestive symbols. Classically, a black hole has no temperature and no real entropy.
So what turned the analogy into physics?
Hawking. He coupled general relativity to quantum field theory and found that the black hole genuinely radiates at a temperature T equals h bar times kappa over 2 pi. That h bar is the tell. It's a quantum effect. It vanishes classically. And once you know the temperature exactly, the proportionality constant in the entropy gets fixed. You land on the famous formula. The entropy equals the area of the horizon divided by 4g Newton, in units where h bar is 1.
The area over 4G. Let me make sure I feel how enormous that is.
You should, because it's staggering. Area is measured in Planck units. The Planck length squared is h bar times g. So for Sagittarius A star, the black hole at the center of our galaxy, the entropy is about 10 to the 85. Even a black hole the size of a proton has entropy around 10 to the 40. If entropy counts microstates, the log of the number of quantum states, then a black hole hides an absolutely colossal number of degrees of freedom behind that horizon.
And classically, there's supposedly just one black hole of a given mass and spin. The no-hair theorem.
That's the puzzle in miniature. No hair says a black hole is characterized by just mass, charge, and angular momentum. So naively, the statistical entropy is zero. There's only one state. Yet the thermodynamics screams 10 to the 85 states. So already, before any paradox, black hole thermodynamics is telling you there's a hidden Hilbert space you can't see in the classical geometry.
Okay, now walk me through where the temperature actually comes from. I've heard pairs near the horizon, but I want the real mechanism.
Let's do it honestly, because it's beautiful. Take the Schwarzschild metric. The line element is minus 1 minus rs over r times dt squared plus dr squared over 1 minus rs over r plus the angular part. The Schwarzschild radius rs equals 2g Newton times the mass. Now zoom into the horizon, change coordinates so that r is close to rs, and expand. When you do that carefully, the near-horizon geometry becomes ds squared is approximately minus rho squared, d tau squared plus d rho squared.
And that doesn't look like a black hole anymore.
It isn't. That's the whole point. Define x0 equals rho times sin tau, and x1 equals rho times cos tau. Plug them in, and the metric becomes minus dx0 squared plus dx1 squared. Plain flat Minkowski spacetime, so an observer freely falling through the horizon sees nothing special. The horizon is a smooth, ordinary point of spacetime. That's the equivalence principle at work. But an observer who hovers at fixed rho, refusing to fall in, is following a uniformly accelerated trajectory in flat space.
And a uniformly accelerated observer sees a temperature. That's the UnRu effect.
Yes, and here's the slick derivation. Take that near-horizon metric and Wick rotate. Set tau equal to I theta and x0 equal to I times x0 Euclidean. Then x0 Euclidean equals rho sine theta and x1 equals rho cosine theta. Those are just polar coordinates on an ordinary Euclidean plane. The accelerated observer at fixed rho is going around a circle of circumference 2 pi rho.
And a periodic Euclidean time is a temperature, the thermal circle.
Precisely. Recall that the thermal partition function is the trace of e to the minus beta h, and beta, the inverse temperature, is the length of the Euclidean time circle. Here, the circle has length 2 pi rho, so the local proper temperature is 1 over 2 pi rho, which equals the acceleration a over 2 pi. That's UnRu. Restore the units and it's h bar times a over 2 pi times k Boltzmann times c.
So the local temperature blows up as our rho goes to 0, right at the horizon. How do I get from that to the temperature someone far away measures?
Through gravitational redshift encoded in the Tolman relation. The proper temperature times the square root of minus g tau tau is constant everywhere in thermal equilibrium. Photons climbing out of the gravitational well redshift, so a place high up in the potential feels colder. You take the local temperature near the horizon, redshift it out to infinity where GTTT is -1, and you find the temperature at infinity is 1 over 4 pi rs. That's the Hawking temperature, what an observer a few Schwarzschild radii away actually measures.
1 over 4 pi-rs, so bigger black holes are colder. A solar mass one is what, 10 to the -7 Kelvin?
10 to the -7 Kelvin, and a lifetime of 10 to the 64 years. Tiny and cold. That inverse relationship matters for your simulations, by the way. In an analog system, your surface gravity is set by how steeply the flow crosses the sonic horizon, and that gradient sets your analog Hawking temperature. The steeper the velocity gradient at the horizon, the hotter and more visible your Hawking signal.
Good, hold that thought. I want to return to the analog mapping later. Let me lock in the Euclidean picture, because it seems central to everything that follows.
'Tis central. Take the Schwarzschild metric and set T equal to I times T Euclidean. You get the Euclidean black hole. Now the crucial thing, to avoid a conical singularity, a sharp point, at r equals rs, you must make the Euclidean time periodic with exactly period beta equals 4 pi rs. The geometry becomes a smooth cigar. The tip of the cigar is the horizon. Far away, it's a cylinder whose circumference is beta, the inverse temperature. And notice this is the same beta we found from the UnRu argument. Inverse temperature 4 pi rs means temperature 1 over 4 pi rs. The two derivations agree, which is a nice consistency check that the thermal circle and the cigar tip are the same physics.
And why must a Euclidean path integral compute a thermal trace in the first place? I want that link airtight.
It's the deepest reason the whole Euclidean method works, so let me make it airtight. Real-time evolution by e to the minus iht is a path integral over Lorentzian spacetime. Analytically continue the time to be imaginary, and e to the minus iht becomes e to the minus beta h, a path integral over a Euclidean geometry evolved for imaginary time beta. Now the trace of e to the minus beta h tells you to set the same boundary conditions at both ends and sum. A strip of Euclidean length beta with its two ends identified is a cylinder, so the thermal partition function is literally a path integral on a Euclidean cylinder of circumference beta. Any correlator you compute on it comes out automatically periodic in imaginary time. That periodicity is the temperature. The black hole cigar is just this cylinder capped off smoothly at the horizon.
Cigar. And smoothness at the tip is what fixes the temperature.
Right, smoothness is the physics, and notice the logic. Far away we fix the length of the thermal circle, and the Einstein equations determine the geometry everywhere else. The Euclidean path integral on this cigar computes the partition function z of beta. It has a gravity piece, e to the minus the classical action, and a quantum piece from the fields. Then you apply the standard thermodynamic identity, S equals 1 minus beta d by d beta, acting on log z, and out pops the generalized entropy.
Which is the next formula I want. Define generalized entropy for me carefully.
The generalized entropy is the area of the horizon over 4g Newton, plus the entropy of everything outside the horizon, matter, gravitons, the quantum fields. In symbols, Sgen equals area over 4h bar g plus S outside. The first term is geometric, the second is ordinary quantum field theory entropy of the stuff in the exterior. And remarkably, this combined quantity obeys a second law. The change in Sgen is always greater than or equal to 0.
So the generalized second law is stronger than the classical area always increases.
Much stronger, and this is important. Classically, the area only grows, but when a black hole Hawking radiates, its area shrinks. That seems to violate the second law. It doesn't, because the radiation carries entropy out. The area goes down, but S outside goes up by more, and the sum Sgen still increases. That's your first hint that the entropy of Hawking radiation is a real load-bearing quantity, not bookkeeping.
Let me pause on a subtlety that always bugs me. That S outside, the entropy of quantum fields right up against the horizon, isn't that divergent? Fields entangled across a surface give an infinite answer.
Sharp question, and yes. There's an ultraviolet divergence from short-distance entanglement across the horizon, proportional to area over the cutoff squared. But, and this is elegant, the same matter loops that produce that divergence also renormalize Newton's constant. 1 over 4g gets a correction of exactly the same divergent form, with the opposite sign. The two infinities cancel, and Sgen comes out finite. It's the usual effective field theory story. The infinite pieces are actually subleading once you remember to use a sensible cutoff.
Beautiful. Okay, now the philosophical linchpin, the central dogma. State it precisely.
Here it is, essentially verbatim from the review. As seen from the outside, a black hole can be described in terms of a quantum system with area over 4g Newton degrees of freedom, which evolves unitarily under time evolution. That's it. From outside, a black hole is just an ordinary quantum system, finite-dimensional Hilbert space, a Hamiltonian unitary evolution, like a hot lump of coal.
Let me push on each word. Area over 4g degrees of freedom. You mean the log of the Hilbert space dimension is the entropy?
Exactly that. It's a statement about the dimension of the Hilbert space. The log of that dimension is the Bekenstein-Hawking entropy. It doesn't matter whether you call them qubits or fermions. What matters is the Hilbert space is finite-dimensional, a finite number of states.
And unitarily, that's the part Hawking denied.
That's the whole fight. Unitary means there's a Hamiltonian, information is preserved, e to the minus iht never destroys a pure state. Now here's the honest caveat the authors stress. These degrees of freedom and this Hamiltonian are not visible in the gravity description. Gravity has a Hamiltonian constraint tied to the whole spacetime. You can't cleanly pull out an exterior-only Hamiltonian. So the central dogma is genuinely a dogma, an assumption about the full quantum gravity theory, strongly supported by string theory, but not derived from the gravity equations alone.
And string theory is where the hard evidence lives?
Yes. For special extremal, supersymmetric black holes, string theorists counted the microstates directly, actual quantum states, and reproduced the area over 4g entropy, including its corrections. That was Strominger and Waffer and what followed. Then add S-CFT, a black hole in anti-de Sitter space, is exactly dual to an ordinary quantum system, a conformal field theory living on the boundary, manifestly unitary, manifestly finite-dimensional at fixed energy. So there are concrete, controlled examples where the central dogma is provably true.
Here's what I don't want to gloss. The review keeps insisting they are not assuming the central dogma. They're providing evidence for it. What's the distinction?
It's a crucial distinction. The fine-grained entropy formulas we're about to discuss are properties of gravity coupled to quantum fields. You can derive and apply them without assuming unitarity. The punchline is that when you compute honestly with gravity, you get an answer consistent with unitarity. So gravity itself is vouching for the dogma, rather than the dogma being smuggled in as a premise. That's why the result is persuasive, rather than circular.
Now, let's get precise about the two entropies you keep distinguishing, fine-grained versus coarse-grained.
This distinction is the heart of avoiding confusion, so let's be careful. The fine-grained entropy, also called the von Neumann entropy, or quantum entropy, is defined from the density matrix Rho as S equals minus the trace of Rho log Rho. It measures your genuine ignorance about the exact quantum state. It's zero for a pure state, perfect knowledge, and it is invariant under unitary evolution. Rho goes to U Rho U inverse, and minus trace Rho log Rho doesn't change. That invariance is exactly why unitarity constrains it so tightly.
And coarse-grained is the thermodynamic one.
Right. For coarse-grained entropy, you only measure a limited set of simple observables. Call them A sub I. You consider every density matrix rho tilde that reproduces your measured values. Trace of rho tilde times AI equals trace of rho times AI. And among all those candidates, you take the one with the maximum von Neumann entropy. That maximum is the coarse-grained entropy. Ordinary thermodynamic entropy is exactly this. Fix a few macroscopic quantities like energy and volume. Maximize over all microstates consistent with them.
And there's an inequality between them.
Fundamental one, the fine-grained entropy is always less than or equal to the coarse-grained entropy. The reason is trivial once you see it. The true Rho is itself one of the candidate rho tildes, so the maximization can only give something bigger. Physically, coarse-grained entropy counts the total number of available states, so it caps how entangled the system can be with anything else. Remember that ceiling, it's the crux of the paradox.
And which one is the Bekenstein-Hawking area entropy, fine or coarse?
Coarse-grained. Here's the giveaway. When a black hole first forms, its area jumps from 0 up to 4 pi rs squared, so the area entropy rapidly increases. But fine-grained entropy of a system formed from a pure state should stay 0, and it's invariant under unitary evolution. It can't just shoot up. So the area law, SBH equals area over 4G, must be the coarse-grained thermodynamic entropy of the black hole. That re-identification is subtle and essential.
Then let me define one more piece, the semi-classical entropy, since it's all over the later formulas.
The semi-classical entropy of a spatial region sigma is the von Neumann entropy of the quantum fields, matter and gravitons, computed on a fixed classical background geometry, by the standard methods of quantum field theory in curved spacetime. In the black hole literature, it's often just called S-matter or S-outside. Key mental model. It's an honest von Neumann entropy, but of the fields living on a frozen geometry. It knows nothing yet about the deep quantum gravity Hilbert space.
Okay, I think we're armed. Give me the Hawking information paradox in its strongest form.
Let's build it. Make a black hole from a pure state, collapse a big, coherent gravitational wave, say. It radiates thermally. Why thermal if we started pure? Because the vacuum of quantum field theory is an entangled state. It's pure as a whole, but the short-distance degrees of freedom are entangled across any dividing surface. The horizon is such a surface, so the outgoing Hawking quantum and its interior partner are created as an entangled pair, pure together, but each one alone is in a mixed, thermal-looking state.
So far, no crime. A complex system thermalizing looks the same way.
Correct, and that's what makes the paradox subtle. Early on, the radiation's von Neumann entropy rises because each escaping quantum is entangled with a partner left behind. If you only had the radiation, it looks thermal, entropy climbing. A hot coal does the same thing in its early radiation. No contradiction yet.
The contradiction is later. Walk me to it.
As the black hole evaporates, its area shrinks, so its coarse-grained entropy, area over 4G, shrinks. Meanwhile, Hawking's calculation has the radiation entropy monotonically climbing because every new outgoing quantum adds a fresh entangled partner inside. Now invoke the inequality. If the total state is pure, the fine-grained entropy of the radiation must equal the fine-grained entropy of the black hole. But the black hole's fine-grained entropy can't exceed its coarse-grained entropy, the area term. So the radiation entropy is bounded above by area over 4G, which is falling.
And Hawking's curve just sails right past that ceiling.
It sails straight through it. The moment when the rising Hawking entropy of the radiation equals the falling Bekenstein-Hawking entropy of the black hole is called the page time. After the page time, Hawking's answer says the radiation is more entangled than the black hole has states to be entangled with. That's mathematically impossible for a unitary quantum system. Either the central dogma is false, information is genuinely destroyed, or Hawking's calculation is missing something.
So Page told us what the curve should look like instead.
Don Page did in the early 90s. If evaporation is unitary, the radiation entropy should rise at first, tracking Hawking, but then turn over at the page time and come back down, reaching zero when the black hole has completely evaporated and all the information is back out in the radiation. That inverted V shape is the Page curve. Hawking's curve rises forever until the black hole vanishes, ending at a large entropy. Page's curve rises, peaks, and returns to zero. Reproducing that turnover is the entire game.
And this is exactly the direction of my project. The cold atom and quantum hardware analogues of an evaporating black hole. The whole point of the evaporation Page curve experiments is to see that entropy rise, peak, and come back down. So when I plot entanglement entropy versus time on the simulator, the turnover at the Page time is the signature I'm hunting.
Exactly right, and it's worth being precise about what Page time means for you. It's the moment the radiation subsystem's entanglement entropy equals the remaining black hole subsystem's coarse-grained entropy. In a finite quantum simulation, that's when the radiation register has accumulated half the entropy budget of the system. The turnover is generic for unitary dynamics on a finite Hilbert space, which is exactly why a genuinely unitary quantum simulator should show it, while a naive semi-classical model won't.
Let me flag the robustness point the paper makes because I think it's underappreciated.
Please, it's important. The paradox is extraordinarily robust. It depends only on general properties of fine-grained entropy, the inequality, unitary invariance, not on the fine details of the Hawking process. So you cannot fix it by tweaking the Hamiltonian a little near the horizon, or adding small corrections order by order. It holds to all orders in perturbation theory. Therefore, any resolution must be non-perturbative in the gravitational coupling G Newton. That's a strong clue. Whatever saves us is a genuinely non-perturbative gravitational effect.
And you can't wriggle out by saying the black hole shrinks, back reaction saves us.
Back reaction, the mass decreasing as it radiates, is already included, and the conflict appears at the Page time when the black hole is still enormous, far from the Planck scale, where semi-classical gravity is completely trustworthy. So you can't blame Planck scale ignorance either. The problem shows up in a regime where we ought to be able to compute reliably. That's what made it a genuine paradox for 40 years.
All right, the resolution starts with a new formula for fine-grained entropy in gravity. Give it to me.
Here's the surprise. Gravity has its own formula for the von Neumann, the fine-grained entropy, not just the coarse-grained one, and it looks almost identical to Bekenstein-Hawking. In spirit, the fine-grained entropy S is the minimum over surfaces of area over 4G Newton, plus the entropy of the fields outside. The only difference from the thermodynamic formula is which surface you use. Instead of the horizon, you extremize.
Extremize how? Make the min precise because I sense it's doing real work.
It is, and there's a nice subtlety. The surface X is codimension 2. It's localized in one spatial direction and in time. You want to minimize the generalized entropy in the spatial direction, but maximize it in the time direction. So really, you look for extremal surfaces, extremize in both space and time. And if there are several, you take the global minimum. Equivalently, the maxim construction. On each spatial slice, find the minimal surface, then maximize over choices of slice.
Write the full formula for me in words, carefully.
Here it is. The fine-grained entropy S equals the minimum over X of the extremum over X of the following bracket. The area of X divided by 4G Newton plus the semi-classical entropy of the region sigma sub X. Here X is the codimension 2 surface, sigma X is the region bounded by X and the cutoff surface far away. And the semi-classical entropy is the ordinary von Neumann entropy of the quantum fields on that region. The whole bracket, area over 4G plus semi-classical entropy, is the generalized entropy evaluated at x.
So the object inside is the same generalized entropy from before, but now we hunt for the extremal surface rather than sitting on the horizon.
Exactly. And the surface that extremizes it is called the quantum extremal surface, QES for short. It's called quantum only because the matter term, the semi-classical field entropy, is included in what you extremize. Geometrically, it's just an ordinary surface in space-time. The recipe: start with a surface out near the cutoff and deform it inward, through the horizon into the interior, looking for a stationary point of the generalized entropy. And critically, the answer depends on the geometry of the interior. Two black holes with identical exteriors but different interiors can have different fine-grained entropies.
That dependence on the interior is going to matter a lot, isn't it?
Enormously. It's the seed of everything. And one more possibility: sometimes the surface can be shrunk all the way down to nothing in the interior. Then there's no area term at all, the vanishing surface. Keep both cases in mind: a non-trivial surface with an area, and a vanishing surface with zero area. The competition between them is the Page curve.
Let's apply it to an evaporating black hole in stages. Start right after it forms.
Right after formation, before any Hawking radiation has escaped, you try to deform X inward, looking for an extremum, and you find none. You're forced to shrink it all the way to zero size. The vanishing surface. Area term is zero, so the fine-grained entropy is just the semi-classical entropy of everything enclosed. If the collapsing shell was a pure state, that entropy is zero. So the black hole starts with fine-grained entropy zero.
Which is exactly right for something made from a pure state, and it's already different from the area, which jumped up to 4 pi rs squared.
That contrast is the whole lesson in miniature. The horizon area is large and growing, but the fine-grained entropy is zero, because the vanishing surface has no area term. Fine-grained and coarse-grained have parted ways, exactly as they should. Now let time run, and let Hawking quanta start escaping.
Now the interior fills up with the trapped partners.
Yes, each escaping quantum leaves an entangled partner behind the horizon. If you keep using the vanishing surface, the enclosed region contains all those lonely interior partners whose outside partners have left, so its semi-classical entropy climbs steadily. This piles up, and it parallels the growth of the radiation entropy. Using only this surface, you'd reproduce Hawking. Entropy growing without bound, the black hole apparently holding more entropy than its area allows. But wait, and here's the turn: a second non-vanishing extremal surface appears shortly after formation. A time of order RS times log of SBH after, in fact. That's the scrambling time. This new surface sits just inside the horizon.
Tell me where exactly, because just inside the horizon is doing something specific.
Here's the construction. Take the time t at which you're computing, go back along the cutoff surface by an amount of order RS times log SBH, the scrambling time, and shoot an ingoing light ray from there. The quantum extremal surface sits close to where that light ray meets the horizon. Note the scales. RS and RS log SBH are tiny compared to the evaporation time, which is of order RS times SBH. So the surface hugs the horizon, and it slides up along the horizon as t advances.
And what's its generalized entropy?
For this surface, the semi-classical field entropy is small. The region it bounds doesn't contain many uncancelled Hawking quanta. So the generalized entropy is dominated by the area term, approximately the horizon area at time t, over 4G. And since the black hole is evaporating, that area is shrinking. So this surface gives a generalized entropy that starts large and decreases, closely tracking the thermodynamic entropy of the black hole.
So now I have two candidates, the vanishing surface, growing from zero, and this near-horizon surface, decreasing from a large value. And the formula says, take the minimum.
Take the minimum. Early on, the vanishing surface wins. It starts at zero and is smaller. Its contribution rises. Meanwhile, the near-horizon surface starts high and falls. At some point, the two cross. That's the Page time. And after the crossing, the falling near-horizon surface is the smaller one, so it takes over as the true fine-grained entropy. The entropy of the black hole therefore rises, peaks, and falls. It follows the Page curve, not by assumption, by minimizing a generalized entropy over surfaces.
Let me make sure I understand the balancing act that makes the near-horizon surface extremal in the first place. Why is it stationary?
Great instinct, because extremal has to mean something. Slide the surface inward along the ingoing null direction. The area is monotonically decreasing as you go in. That's geometry. But the semi-classical entropy is not monotonic. Start with x right on the horizon and push in. At first, the newly included interior modes purify the outgoing quanta you'd already enclosed, so the entropy decreases. Once all those are purified, pushing further starts, including modes entangled with quanta still outside the black hole region, so the entropy starts increasing again.
So there's a sweet spot where the falling area and the turning around entropy balance.
Exactly. The point where the decrease in area from a small deformation is exactly cancelled by the change in the semi-classical entropy. That's the extremum in every direction, not just the null one I described. The foolproof balances the area variation against the entropy variation in all directions. But the null direction picture gives you the honest intuition. Area always wants to shrink, entropy has a minimum, and the QES sits where their sum is stationary.
Beautiful. So the black hole's own entropy follows the Page curve. But you warned me earlier, that's not yet the information paradox, which is about the radiation.
Correct, and this is the pivotal move of the whole review. The paradox is phrased in terms of the entropy of the Hawking radiation, the stuff way outside, collected far from the black hole. Naively, you'd compute its semi-classical entropy, S semi-classical of the radiation region, and that just grows and grows, a la Hawking. The radiation lives where gravity is negligible. You could imagine dumping it all into a giant quantum computer far away. So why would gravity have anything to say about its entropy?
Right, that's my instinct too. The radiation is out in flat space. Why apply a gravitational entropy formula to it?
Because of how the state was made. The radiation state was produced by a gravitational process, evaporation. And it turns out the correct rule is to apply the same gravitational fine-grained entropy formula, even to a region that contains no black hole. The formula's spirit is, vary the region by moving the surface x to minimize the entropy. And here's the new ingredient. We allow the region whose entropy we're computing to be disconnected.
Disconnected. That's the island. Explain why disconnected regions would ever help.
Think about the trade-off. Making the region disconnected adds a new boundary, hence more area. That costs you in the area over 4G term. So you'd only do it if it buys you a bigger decrease in the semi-classical entropy. When could that happen? When there's some faraway region whose fields are entangled with your radiation. Including it would purify the radiation, dropping the semi-classical entropy. And that is exactly the situation with Hawking radiation. It's entangled with the fields in the black hole interior.
So you reach back in and grab a piece of the interior, an island, to purify the radiation.
You grab the interior, write the island formula. The fine-grained entropy of the radiation, SRAD, equals the minimum over x of the extremum over x of the area of x over 4G Newton, plus the semi-classical entropy of the union of the radiation region and the island region. The area is the area of the boundary of the island, and you extremize and minimize over the island's location and shape. The island is a disconnected region inside the black hole whose boundary is a quantum extremal surface.
I want to flag the notation trap the authors themselves warn about. Rad is on both sides of the equation.
Yes, and they say it's caused much confusion and heated complaints. I love that they admit it. The left side, SRAD, is the true, full, fine-grained entropy of the exact quantum state of the radiation, the thing produced by the real theory of quantum gravity. The right side uses the semi-classical state, radiation plus island fields on the fixed background. Those are different states. The magic is that the formula computes the entropy of the exact state using only quantities from the semi-classical state. It doesn't hand you the exact state, just its entropy.
So the formula is a bridge, semi-classical inputs on the right, exact fine-grained entropy on the left.
That's the perfect way to say it, and that's precisely why it's so powerful and so surprising. You never need to solve quantum gravity to get the entropy right. Now let's run the two contributions, just like before.
Contribution 1, no island.
The simplest option is no island at all. Then the formula just gives the semi-classical entropy of the radiation, which grows as more Hawking quanta escape. That's the rising Hawking-like branch. It's always a valid extremum, but it won't always be the global minimum.
Contribution 2, with an island.
A non-trivial island appears a scrambling time, Rs log SBH, after formation. It's centered on the origin, and its boundary sits just inside the horizon, the same quantum extremal surface as before. The generalized entropy now has the area term, roughly the black hole's area, plus the semi-classical entropy of radiation union island. But that combined entropy is small, because the island contains the interior partners that purify the outgoing radiation. So this branch is dominated by the area term, which starts large and decreases to zero as the black hole evaporates.
And you take the minimum of the two branches, and you get the Page curve for the radiation.
You get the Page curve for the radiation. The rising piece is the no-island branch. The novel falling piece is the island branch. Before the Page time, there's no island. The radiation entropy rises. After the Page time, the island switches on, the interior gets included, and the entropy falls back towards zero. Same inverted V, now for the actual radiation whose entropy defines the paradox. The paradox is resolved.
And let me confirm the consistency check. Black hole entropy and radiation entropy should be equal if we started pure.
They come out equal, and the reason is clean. In both computations, the same surface X appears. And when the matter state is pure on the full slice, the semi-classical entropy of sigma X equals the semi-classical entropy of radiation union island, because the complement of a region has the same entropy as the region for a pure state. So you're extremizing the identical function, and you get the identical answer. Black hole and radiation ride the same Page curve, consistent with purity as required.
Now, the skeptic's objection, which I feel in my bones. You just decided to include the interior. Of course you get a pure state if you throw the interior back in. It's an accounting trick.
This is the objection that has to be answered, and the review answers it head-on. We did not include the interior by hand. The island formula is derived from the gravitational path integral, through a method conceptually just like Gibbon's and Hawking's derivation of black hole entropy from the Euclidean cigar. It is gravity itself that instructs us to include the interior. Gravity is telling us evaporation is unitary without handing us the microscopic state. The island isn't a choice, it's what the extremization forces on you when the island branch has lower generalized entropy.
There's a lovely analogy in the paper, the paintings.
The paintings, yes. Picture a man with a house full of expensive paintings. He borrows money from the townspeople, using the paintings as collateral, and throws lavish parties. Eventually, he's borrowed so much that most of the house and its contents legally belong to the townspeople. When the townspeople tally their wealth, they must count the paintings in his house, even though the paintings physically sit in his home. But he cannot count them as his own anymore.
Map it for me.
The house is the black hole interior. The wealth is quantum information. The townspeople are the faraway radiation. As evaporation proceeds, the interior, the paintings, comes to belong to the radiation, even though it's physically located behind the horizon. So when you compute the radiation's entropy, you must include the interior island, just as the townspeople must count the paintings. Anyone who looked only at the radiation and called it thermal would be as wrong as someone who called the townspeople poor for having bare walls at home.
That reframes everything. So what does this say about where the black hole interior actually lives?
This is the entanglement wedge story, and it's profound. The degrees of freedom in the central dogma, the ones describing the black hole from outside, describe the region of spacetime out to the quantum extremal surface. That region is called the entanglement wedge of the black hole. Before the Page time, the QES is the vanishing surface at the origin, so the black hole's entanglement wedge is the whole interior. The black hole degrees of freedom describe everything inside.
And after the Page time?
After the Page time, everything shifts. The QES is the non-trivial surface near the horizon, and now the interior splits. the black hole degrees of freedom describe only the sliver between the cutoff and the QES, a portion of the interior. The rest of the interior, the island, is described by the radiation. The interior has been encoded into the Hawking radiation far away. That's the resolution. Most of the old black hole interior is, quite literally, part of the radiation's Hilbert space.
So the transition point in the page curve isn't just an entropy kink, it's the moment the interior changes owners.
Beautifully put, and the authors stress exactly this. Language is a poor guide here. The turnover from rising to falling entropy is precisely when most of the interior stops being described by the black hole degrees of freedom and starts being described by the radiation. The entanglement wedge of the black hole shrinks. The entanglement wedge of the radiation grows to swallow the interior. And there's a hypothesis making this operational: entanglement wedge reconstruction.
Which says
That if some qubits sit inside the entanglement wedge of a system, you can in principle recover their state by operating only on that system's degrees of freedom. So after the page time, information that fell into the island can be reconstructed from the radiation alone, via an explicit map called the Petz map, which in simple gravity theories can even be built from the gravitational path integral using the replica method. The catch: the required operations on the radiation are absurdly complex, with a complexity roughly exponential in the black hole entropy. Recoverable in principle, hopeless in practice.
this also resolves an old Wheeler puzzle, doesn't it? The bag of gold.
It does elegantly. Wheeler noted you can build geometries that look like a modest black hole from outside, a narrow neck, but hide an arbitrarily large interior bag full of entropy, more than the neck's area allows. Puzzle, doesn't that violate area over 4G bounding the entropy? Resolution, the black hole's entanglement wedge only reaches the QES at the neck. It does not include the giant interior bag. So the fine-grained entropy seen from outside is just the neck area over 4G. The excess interior entropy simply isn't described by the exterior degrees of freedom. An evaporated black hole after the page time is itself rather like a bag of gold.
Okay, now the piece I most want the real mechanism for: replica wormholes. Where does the island formula actually come from in the path integral?
Let's do it. And it's genuinely one of the most beautiful arguments in the subject. The tool is the replica trick, which computes von Neumann entropy when you can't get at the matrix rho directly. The idea: compute the trace of a rho to the nth power for integer n, then analytically continue in n, and use s equals 1 minus n, d by dn, acting on log of trace rho to the n, evaluated at n equals 1. That derivative at n equals 1 gives minus trace rho log rho.
So the whole thing reduces to computing trace of rho to the n in gravity.
Right, and let's warm up with the simplest case, n equals 2. The purity, trace of rho squared. Here's the diagnostic. If rho is a pure state, trace of rho squared equals the square of trace rho. If a rho has large entropy, highly mixed, then trace of rho squared is much less than the square of trace rho. So the purity tells you pure versus mixed. We want to know whether the final radiation is pure.
How do you build our rho from the gravitational path integral?
Start with the initial pure state, a collapsing star. Evolve with the gravitational path integral to get the amplitude to reach a particular final radiation state, the overlap of J with psi. The density matrix R rho is the ket psi bra psi, and its matrix elements R rho ij are I with psi times psi with J, each computed by a gravitational path integral. To get trace of R rho, you set the final bra and ket states equal and sum. That glues the diagram into one closed geometry.
And trace of rho squared glues two of these together.
2 copies, cross-identified. And now the decisive gravitational point. In gravity, you must sum over all space-time topologies, all the ways of connecting things. So when you compute trace of rho squared, there are different ways to connect the 2 copies' interiors, and you sum over them. 2 saddle points dominate. The first, the Hawking saddle, keeps the interiors disconnected. Follow the identifications, and it gives Hawking's answer. Trace of rho squared much less than the square of trace rho. Large entropy.
And the second saddle?
The second is the replica wormhole, a geometry where the two black hole interiors are joined through the bulk, a wormhole connecting the replicas. When you evaluate it and rearrange the diagram, it gives trace of rho squared equal to the square of trace rho exactly. Zero entropy, a pure state. So there are two competing geometries, the disconnected Hawking saddle giving large entropy and the connected replica wormhole giving zero entropy.
And the path integral takes whichever dominates.
Whichever has the larger contribution. Early on, the Hawking saddle dominates and you get rising entropy. Late, after the page time, the replica wormhole dominates and you get the unitary answer, entropy coming down. The transition between which saddle wins is exactly the page time transition, and it's exactly the same as the switch between the no island and island contributions. The replica wormhole is the microscopic mechanism behind the island. The island is the wormhole's shadow in the entropy formula.
Let me make sure I see how the general N calculation lands you back on the quantum extremal surface, not just on the purity.
Let's trace it. For general N, you compute trace of Rho to the N, and gravitationally, that's a path integral with AN copies of the exterior, glued cyclically, copy 1's bra to copy 2's ket, and so on around the loop. Then you sum over how the N interiors connect, the fully disconnected way, each interior capped off on its own, like N separate cigars, reproduces Hawking. The fully connected way, the replica wormhole joining all N interiors, is a single smooth N-fold geometry. When you evaluate that connected saddle's action and analytically continue N down toward 1, using S equals 1 minus ND by dN, acting on log trace rho to the N derivative localizes onto a codimension 2 surface, the fixed point of the replica symmetry, and the area of that surface over 4G is exactly what appears. That surface is the quantum extremal surface, and the leftover matter piece is the semi-classical entropy. So the replica wormhole, continued to N equals 1, literally derives the area over 4G plus semi-classical entropy formula from scratch.
So the area over 4G isn't put in. It falls out of the replica symmetry fixed point.
It falls right out, and that's the punchline of Lukowicz and Maldacina's argument that underlies the whole edifice. The conical deficit from the N-fold cover concentrates at the fixed point surface, and Einstein's equations turn that deficit into precisely area over 4G. The minimization over surfaces and the mine of the two saddles is just the statement that the path integral is dominated by whichever geometry has the smaller action. Everything, the area law, the extremization, the page curve turnover, is downstream of sum over topologies, keep the dominant saddle.
So the island and the replica wormhole are two descriptions of one phenomenon.
Precisely two faces of the same coin. For general N, you consider N copies and all the ways of connecting the N interiors. Fully disconnected gives Hawking. Fully connected, the replica wormhole, gives, after continuing to N equals 1, the quantum extremal surface answer. You take the minimum and out comes the page curve. And notice the deep echo. This is conceptually the same as Gibbons and Hawking computing black hole entropy from the smooth Euclidean cigar. In Euclidean signature, the Hawking saddle is two separate cigars. The replica wormhole joins them through the interior.
Let me connect this hard back to my simulations, because now I think I understand what I'm and what I'm not reproducing.
Good. Let's be careful and honest about the mapping. Your cold atom or quantum hardware analog is a genuinely unitary quantum system. When you partition it into black hole and radiation and watch the entanglement entropy of the radiation register, unitarity guarantees the page curve turnover, rise, peak at the page time, fall to 0. That's the finite Hilbert space, unitary fact that Page proved. Your simulator reproduces the left side of the island formula, the true fine-grained entropy, honestly, by direct quantum evolution.
Whereas the gravity side, the islands, the replica wormholes, those are how a semi-classical observer recovers that same curve without access to the microstate.
Exactly the right split. In your simulator, you have the microstate. You can just measure the entropy and see the turnover. There are no islands, no wormholes, because you're doing the exact unitary evolution. The island formula's whole achievement is getting that same curve from the semi-classical gravity description, where you don't have the microstate, So your experiment is the ordinary quantum system of the central dogma made concrete. It's the thing the black hole is conjectured to be equivalent to. Demonstrating the turnover on hardware is a direct, tangible check that unitary evolution yields the page curve.
And the analog horizon, the sonic horizon in a flowing condensate, gives me the Hawking pair creation to feed that entropy.
Right. In the analog, phonons play the role of the quantum fields. The sonic horizon, where the flow exceeds the speed of sound, splits phonon pairs just like the gravitational horizon splits the vacuum. One phonon escapes upstream, its partner is trapped downstream, an entangled pair, exactly the outgoing and interior Hawking quanta. That entanglement is what makes the radiation register's entropy climb. If you can also mimic evaporation, draining the black hole region's degrees of freedom into the radiation, you get the full rise and fall. That's the evaporation, page curve direction of your work in one sentence.
Let me raise the firewall business because I know it's lurking. The AMPS paradox. How does the island story deal with it?
Briefly, because it's an appendix in the review, but conceptually important. AMPS, Almheiri, Marolf, Polchinski, Sully pointed out an apparent contradiction after the page time. A freshly outgoing Hawking quantum seems forced to be maximally entangled with two different things at once, its own interior partner and the early radiation. Quantum mechanics forbids that, monogamy of entanglement. Their proposed fix was drastic. Break the entanglement with the interior partner, which puts a firewall of high-energy quanta at the horizon, destroying the smooth interior.
And this review says no firewall.
No firewall. AMPS smuggled in an extra assumption beyond the central dogma, that the interior is described by the same degrees of freedom as the exterior. This review drops that assumption. After the page time, the interior partner is not a separate system. It's part of the early radiation because the interior is in the radiation's entanglement wedge. So there's no double entanglement, no monogamy violation. The outgoing quantum's partner and the early radiation it's entangled with are the same thing. Monogamy is respected and the horizon stays smooth. That's the resolution the island picture gives.
I want to be a good scientist and hear the caveats. What does this program not yet do?
The authors are admirably candid, so let's list them honestly. First, reproducing the page curve gives you the entropy, a trace of a function of RHO, but not the individual matrix elements of RHO, nor the S-matrix. You learn that the radiation is pure, but not the precise quantum state, nor how a given initial state maps to a given final state. Computing individual amplitudes directly from gravity, without a holographic dual, is still open.
So information comes out, but here's exactly how to read it out is unsolved.
Right. There's a formal recovery map, the PETS map, and the slogan that very complex operations on the radiation weave their own space-time that reaches back to the interior. But it's not a practical or fully understood readout. Second caveat, these derivations lean on the Euclidean gravitational path integral, and it's genuinely unclear how to define that precisely, which saddles to include what the integration contour is. It's even possible that in some theories, replica wormholes contribute and black holes are unitary, while in others they don't and Hawking's picture survives. The authors suspect the latter theories would be inconsistent, but it's not proven.
And the imaginary cutoff surface bothered me too, the place where they froze gravity.
It should bother you. It's the third caveat. The derivation draws an imaginary surface a few Schwarzschild radii out and treats spacetime as fixed beyond it. A complete treatment would let gravity fluctuate everywhere. The best understood case is when that cutoff is the boundary of anti-de Sitter space, where holography gives full control. For a real asymptotically flat black hole, exactly where to put the surface, and whether the central dogma holds at finite distance isn't fully settled. Though they note this isn't much worse than the standard subtleties in defining Gibbons-Hawking entropy in flat space.
There's also a tantalizing line about cosmology.
Yes, our universe has a cosmological horizon from accelerated expansion, and it too has a Gibbons-Hawking entropy and a Hawking temperature. It's tempting to apply all of this, islands, fine-grained entropy, to cosmological horizons. But it's genuinely unclear whether a cosmological horizon is a quantum system in the central dogma sense, the way a black hole seems to be. That's frontier territory, and honestly relevant to how far one might push analog horizon simulations conceptually.
Let me try to give the whole arc back to you in one breath, and you correct me.
Go for it.
Black holes are thermal, temperature h-bar kappa over 2 pi, entropy area over 4g. That coarse-grained entropy suggests a hidden Hilbert space, the central dogma. From outside, a black hole is a unitary quantum system with area over 4g states. Hawking's calculation of the radiation's von Neumann entropy rises forever, crashing through the falling area bound at the page time. Impossible if unitary. The fix? Gravity has its own fine-grained entropy formula, minimize over quantum extremal surfaces of area over 4g plus semi-classical entropy. Applied to the radiation, it forces you to include an island in the interior after the page time, which purifies the radiation and turns the entropy over. And the whole thing is derived from replica wormholes in the gravitational path integral.
That's essentially perfect. I'd add just one emphasis. The reason it's a resolution and not a trick is that gravity itself, through the path integral and its sum over topologies, is what dictates including the island. You don't put it in by hand. And the byproduct is a radically new picture of the interior. After the page time, most of it is encoded in the radiation, not in the black hole. The entanglement wedge tells you who owns which piece of space-time.
And the single sentence I should attach to my project.
Your simulator is the ordinary unitary quantum system that the central dogma claims a black hole secretly is. And the page curve you're chasing, the entanglement entropy that rises, peaks at the page time, and falls back to zero, is the direct experimental signature that black hole evaporation conserves information. The island formula and replica wormholes are how theorists recover that same curve from geometry alone. You get to see it happen dynamically in a lab.
One more precise thing before we close, because I'll be asked, why is the scrambling time, RS log SBH, the delay before the island appears?
It's a lovely detail. The scrambling time is how long a chaotic quantum system of entropy S takes to spread, scramble, localized information across all its degrees of freedom. For a black hole that's RS times log SBH, the island physically is the statement that the interior information has become reconstructible from the radiation. That can only happen once the black hole has had time to scramble a bit of information out. So the log S delay isn't arbitrary, it's the black hole's scrambling clock, and it's the same time scale that shows up in quantum chaos diagnostics like out-of-time order correlators. If your simulator is chaotic, you'll see the island's analog switch on, after roughly a scrambling time too.
That's a concrete handle. Last question. If I had to name the single most surprising equation in the whole review, what is it?
Without hesitation, the island formula SRAD equals the minimum over x of the extremum of area of x over 4g, plus the semi-classical entropy of radiation union island. Surprising because rad is on both sides, because it drags a piece of the black hole interior into the entropy of radiation collected light-years away, and because it computes the exact quantum entropy purely from semi-classical data. It says gravity quietly knows about unitarity, even when the naive calculation screams the opposite. That one line is the resolution of a 40-year paradox.
George, this was exactly the rigor I wanted. I now know what curve I'm reproducing, why it turns over, and what it's really telling me about where information lives.
My pleasure, Alice. Go find that turnover on your hardware. When the radiation entropy peaks and comes back down, you'll be watching, in a cold cloud of atoms, the same physics that resolves the Hawking information paradox. That's a remarkable thing to hold in your hands.
Let's build it. Thanks, George.
Anytime. Keep the math out loud. It's how the confusion dissolves.